Okay, thank you very much for those introductions. It's wonderful. I also want to, so there are several times in our research where things that are really spectacular and special happen, and there's been a couple in the high energy physics group, discovery of the top quark, the discovery of B sub S mixing. Both of those happened before I arrived, but this is one of these moments where something truly spectacular has happened, and it's really the result of a lot of hard work by a lot of people, and I'm just here telling you about it. So my talk, I really want to be take a sort of celebratory tone, and I want to thank you for, I mean, this is wonderful. In the summer, having so many people, I want to thank you for showing up and listening to what I have to say on this. I also want to say I did give a colloquium recently, a few months ago, back in April, on this very subject where we had sort of the first hints of this, of something special going on in our data. So I'll try not to repeat too much of that, but you can tell that there's something sort of special that has happened since, given that I'm wearing a tie in July and I don't usually wear ties. So this is a really special occasion. Okay, so let me just dive right in here. Okay, so the pursuit in our field in particle physics, what we're trying to do is, our pursuit is to understand the universe. It's really quite a tall order. Understand the universe at its most fundamental level, including the basic constituents of matter and their interactions. It's a bit of an ambitious goal. We have tools in order to make this determination, in order to study the universe at its most fundamental level. And one of the main techniques we have are particle accelerators that can probe into the structure of matter and understand how the matter particles interact with each other. And so we might take some substance and look closer and closer with higher and higher energy particle probes. And eventually we can discern that there's, within a substance is composed of atoms, and inside those atoms are a nucleus comprised themselves of nucleons forming protons and neutrons. And in fact, we now know inside the nucleons themselves are really comprised of a really complex system of quarks and gluons and fluctuating energy density and so forth. But as far as we know right now, we haven't seen anything more fundamental than the quark, so we sort of have a question mark left here, but this is the pursuit where we're looking at finer and finer detail with increasing energy. So particle accelerators are really like big microscopes. There's actually quite a bit of relation to understanding of the universe more generally, and the origin of the universe and the evolution of the universe. So as you know, our current theory is that the universe started in some enormously energetic space-time singularity we call the Big Bang. There was a period we call inflation, which had this sort of superluminal expansion of the space-time, which in fact may have something to do with the Higgs field itself. I won't go much into that unless you ask. And then we had this sort of primordial soup of particles and fundamental particles and energy. And then the universe, of course, expanded and cooled and got to a point where we were able to form the first what we call hadrons, which were mesons and baryons. And eventually we were able to have, it was cool enough that the first atoms can form. And when that happened around 300,000 years ago, it left an imprint called the cosmic microwave background on the sky, which shows temperature fluctuations consistent with that epoch, so we can use that to study it. And then eventually the universe cools and expands and we form galaxies, and it's really gravity that clumps everything together, but the fundamental, but gravity, the fact that things clump together not only has to do with the curvature of space-time, but the fact that there's mass and energy density. And so mass is a very fundamental property of the universe, and it really allows us to form life as we know it, because everything, if nothing has mass, everything is moving around the universe with the speed of light. And so the origin of mass is a real puzzle, and it really goes at the heart of what's going on in our universe. So particle colliders allow us to look back in time. So if you actually look, there's a few lines here that show what our present experiments, terrestrial experiments in colliders, can probe in terms of energy densities, which really are about probing physics backwards in time. And so here you see the Large Hadron Collider. We can peer back at this very early time in the universe's evolution. So the particle colliders really allow us to look, they're little time machines. And also I just want to make the point that the largest and smallest things in the universe are really intimately linked. So the fruits of our labor in studying fundamental particles and their interactions over many, many decades is something we call the Standard Model. So you hear a lot about the Standard Model. It's basically a model that describes fundamental particles of matter and their interactions with each other. It's a relativistic quantum field theory based on a specific gauge symmetry group, and I'm not going to go into details about the mathematics of this of the standard model, but you do need to understand a little bit of this, or we have to touch on it to really understand the Higgs field. So there's a particular symmetry group which is just a set of rules, a mathematical set of rules for how particles interact with each other and what the particle content is. And so there's the symmetry group, we call this. All matter in the standard model is comprised of fundamental particles. In quantum field theory, they're representative of fields. And that standard model describes interactions amongst these particles. And it really has been, its current form of the standard model is essentially completed around the 1970s. That was when QCD really, in its final form, was put into the theory. And this is a theory that stood up against experimental scrutiny for 40 years, with the only real verifiable deviation from the standard model being in the neutrino sector, discovering neutrino mass and mixing. So I want to spend a little time on this slide because we need to, in order to really understand the story, we need to understand the players. And in the players in the standard model are the quarks, the leptons, and the forces, which are really, we call them intermediate vector bosons. And it's the quarks and leptons that form matter, and the forces, and they interact with each other by exchanging these quanta, which are the force-carrying particles. So ordinary matter is comprised of 6 quarks and leptons. Many of these are familiar to you, like up and down quarks, which bind together to form protons. We have the charm and strange quark in the top and the bottom quark. And the top quark, members here, especially Tony List, played a critical role in the top quark discovery in 1995. And the mass has sort of increased as we go further down this, the family chain here. So the top quark is by far the most massive particle we've ever discovered. And the bottom quark has a lot of interesting properties that Professor Pitts has studied. And then we have the leptons, which are, so the quarks combined together, they feel what we call the strong force. They have a quantum number called, they have a quantum called color. And they feel the strong force, and they're also charged, they're fractionally charged. And then we have the leptons here, which are, we have the charged leptons that don't feel the strong force. And we have the neutral leptons that are nearly massless. We've now only recently discovered that they have mass, actually. So this comprises ordinary matter, and the interactions among these particles are mediated by these force-carrying particles themselves. And in fact, the force-carrying particles can interact with themselves. Okay. These are, so the force-carrying particles, we have the gluon, which mediates the color force amongst quarks. We have the binds quarks together inside nucleons. We have the photon that mediates the interactions amongst electrically charged particles. And we have these 2 particles called the W and Z. There's actually 3 particles, W and plus W minus and Z, that mediate the weak interaction, which is what really plays a role in nuclear beta decay and nuclear decay. So we have this kind of picture here, and these are what we call bosons. They're integer spin particles. And these are fermions, they're spin 1/2 particles. And that has to do with how there are some symmetry properties under particle exchange that I won't go into detail. But we have these 2 classes of particles called fermions and bosons. And then there's this thing at this, okay, so in terms of masses, in fact, what we know now, what we know at the current energies we observe the universe at, we know that the mass, the photon and the gluon are massless. But we know that these are very, very heavy. They have masses that are, the top quark mass is about 173 GeV. A GeV is roughly the mass of a proton. And the W and Z particles are like 80 and 90 GeV. So they're very massive force carriers. All the other force carriers are massless, but these force carriers carry mass. And that has, that's really a challenge for the theory to describe how that comes about. And then there's this guy at the center of everything called the Higgs boson, and I'll assure you I get back to that guy. But every one of these particles has been directly observed in experiments, mainly at colliders. But of course, some like the electron, of course, was observed before. But in terms of the heavier particles, they were just observed at colliders. The only one that hasn't been observed is this Higgs particle. And I want to mention the standard model is a theory which describes the strong interaction among quarks, the weak interaction and electromagnetic interaction, but it doesn't describe gravity. So the standard model is a theory with some assembly required, gravity not included. Okay. A little bit more about this electroweak symmetry. Now, the weak and the electromagnetic forces are described by a single electroweak interaction, which is, if you look, this is the sort of the last 2 parts of that symmetry group that I described for you. So what that means is that if we actually observe the universe at high enough temperature, that is early enough in the universe's evolution, we'd actually see that the weak force and the electromagnetic force really have the same coupling strength. It's only at lower temperatures that a sort of phase transition happens where they break into two different forces. Also in this theory, the particles are massless. They have no mass in the theory of the Standard Model. And that is required to preserve what we call a property which is a guiding principle in the development of any quantum field theories, which is called gauge invariance. And I won't go into more details, except for to say that it's a property for which you sort of have the same measured quantity across everywhere in a field. It's a very important property in particle physics. Okay, so these are the 2 points. We have a single electroweak interaction at high temperature, high energy density, and we have the particles in the Standard Model must be massless in order to preserve this tenet of the Standard Model called gauge invariance. So that's the mathematics of the theory require these. But we know that the electromagnetic force is much stronger than the weak force, just experimentally. And we know that the weak force carriers actually have mass, the W and Z. And we know other particles have mass too. So sort of there's this tension where we require this for the mathematics of the Standard Model to work, but yet we know that the electromagnetic and the weak force have different strengths, and we know that particles are indeed massive. So that's a real question. This hung up the theory for quite a few decades, is try to understand what is it that breaks electroweak symmetry that's required of the Standard Model. And a related question, which is what is the origin of mass, which is a very fundamental question, as I mentioned, because otherwise, if no particles have mass, then they just move around the universe at the speed of light. They don't clump together and form you and I. So what does this? What is the agent of electroweak symmetry breaking? And I wanted to mention that, in fact, so I was going to say it in the beginning, but in fact, everything I'm talking about electroweak symmetry, as sort of Dale alluded to, was known by the condensed matter theory field for a very long time. So particle physics is sort of just catching up, but you have to kind of give us a break there. So about electroweak symmetry breaking, what is this agent of electroweak symmetry breaking? Well, what we hypothesize is that in the Standard Model description of electroweak symmetry breaking and mass generation is that the entire universe is filled with some invisible scalar, that it's a spinless quantum field, that it pervades everywhere, and it's a quantum field called the Higgs field. And what we really need now, if we hypothesize we have this Higgs field, this quantum field, this scalar field, we still need a way to break electroweak symmetry and give masses to the elementary particles, but preserve this symmetry we call gauge symmetry. And the way we do that is something called the Higgs mechanism. So the Higgs field has a non-zero value everywhere. Here are the two ingredients. Even in its lowest energy state, even in its ground state, it still has a non-zero value. So we call that it has a non-zero zero-point energy. So it has a vacuum excitation value. We then allow, so that's ingredient one. That's the property of the Higgs field itself. We then allow the massless gauge particles to interact with the Higgs field. So we take all these massless particles that are in the Standard Model, we allow them to interact with this field, the Higgs field that has this non-zero vacuum excitation value. And what happens is some miraculous things happen. And again, this has been known from the condensed matter theory side for a long time. Is that one, but in the application to particle physics, electroweak symmetry gets broken just spontaneously, just through these two things. No external agent like a magnetic field or something is required to break the symmetry. It happens spontaneously. Massless particles acquire mass. So some of the degrees of freedom that are in the Higgs field actually get eaten up and become part of that lead to masses of the particles. And the third thing that happens is that we're left with this quantum of the Higgs field, which is a massive scalar boson. It's a spin-zero boson. It's called the Higgs boson. So the Higgs boson is the physical manifestation. It's an excitation of the Higgs field, which breaks electroweak symmetry and gives particles masses. And this is actually the simplest way in the Standard Model to break electroweak symmetry and give masses to the particles. There are many other ways to do it, but the Standard Model is sort of Occam's razor. It's the simplest one. I think for time I won't go through all this, but there's a very rich history in this. And so really we borrowed a lot. That really started for us at least to borrow a lot of this from Phil Anderson's work in superconductors, which of course build on work from Nambu and Schwinger. In particle physics, so this is where Anderson sort of had this identifying the superconductor, that there are these Goldstone called plasmon modes. But really this was not a relativistically invariant theory. And what these guys did, Englert, Broad, Higgs, Grolnick, Hagen, and Kibble, what they did is they showed that this mechanism can be applied to a relativistically invariant theory, which is really required of the particle of the standard model, that it be relativistically invariant because we're dealing with relativity. And there's a whole bunch of papers here. And then actually this was shown that the role that this kind of thing plays in electroweak symmetry and in the standard model development was really picked up by Weinberg and Salam. So I just wanted to show you some of these. So this is a very important work. And in fact, here are the 6 physicists. And they won the sort of the prestigious in particle physics theoretical award called the Sakurai Prize. And so there's Higgs and there's the others. And here they won it for elucidating the properties of spontaneous symmetry breaking in 4-dimensional relativistic gauge theory and the mechanism for the consistent generation of vector boson masses. Okay. So we remember we were left with this. What we needed was a way to break electroweak symmetry, which you know is broken, and also give masses to particles, which we know they have. And what this turns out to be now, the signature is really about finding this guy, finding the Higgs boson. So there's this little, this little wanted poster, wanted for SU2 cross U1, which is the electroweak symmetry group, breaking. If you find him, call the Nobel Prize Committee, and then there's a $200 award, which I made the joke in my colloquium, but there's like 7,000 people looking for this thing, and the award's 1.4 million, so I'm going to be waiting for my $200 check in the mail. Okay, so where should we look for the Higgs? Well, our theorists actually tell us where to look in order for the theory to be valid, not just at the energies of normal experience, but at the energies way beyond almost imagination, up to unimaginable energies we call the latest here, which is called the Planck scale, in which quantum gravity becomes important. So quantum effects of space-time itself become really, gravity becomes in some sense strongly coupled at that level. So where should we look for it? Well, they're given sort of a range. So you see, in order for this, there's this sort of like, we call it a throat plot, which is that bad things happen down here. So what I'm showing is the Higgs mass versus this energy scale in the standard model. So if we run the standard model up to high energy scale, we're left with this region here. Bad stuff happens up here. We call it the triviality bound, where the Higgs no longer interacts with anything. And bad stuff comes down here. We call it the stability bound, where the vacuum itself becomes unstable and really bad stuff happens. So we have sort of this region here where we can really accommodate the standard model Higgs. Otherwise, there's a breakdown of the standard model theory at high energy. So that's from the theory end. You can ask, well, where do we look for the Higgs? Well, there are many ways to look for the Higgs. In fact, often we see, there's so many hints and rumors that we often see some sightings. So here's a sighting at CERN, where we're sighting of the Higgs field, and this person looking here very much like an agent. So maybe the question is this the agent of electroweak symmetry breaking? And so you see these sightings and rumors. It's a big deal to find the Higgs. But as far as more practically than just sort of looking around CERN, how do we find the Higgs? Well, one of the things we do is we smash stuff together really, really hard. And not only that, but we do it a lot of times because we're talking about very rare processes, and so we have to really smash stuff together at high energy and really hard. And it's sort of like how children learn, at least mine do, by smashing stuff together and seeing what comes out. It's not unlike that. But our stuff is not the cars, it's actually hadrons, that is, protons or antiprotons at the Tevatron, which are smashed together at very high energy. So they're accelerated using very powerful magnets at highest available energies and focused to collide at a single point in space. And then one of the wonderful gifts from Einstein is the fact that we can focus, the available energy in these beams, in these hadron collider beams, can be used to form new forms of matter, like the Higgs boson. So we can smash them together really hard, give them lots of energy, and that energy is converted into producing new forms of matter. Maybe a Higgs boson here. One of the challenges we have, though, in finding, it sounds pretty simple. We just smash stuff together very often. We look for, and then we just, almost like stop the experiment, go into the detector, and see if there's any Higgses there. Unfortunately, it doesn't work that way. The challenge is really that when we produce these very heavy particles, they're extraordinarily unstable, and they decay almost immediately. So the Higgs boson, we don't actually ever discover the Higgs boson. What we do is we look for signatures in decay products. So the Higgs decays in certain ways. Finally, it decays to state particles that are stable enough to be seen in our detector. They move away from our detector. They move outward from the interaction point. But we really look for these signatures. And it's difficult not only because they decay, but also the signatures that they leave behind often look like things that are not what we're really looking for, like more mundane physics that we're not trying to discover. So that's one of the challenges. So when you look at what I'll be showing next is we're really talking about looking at signatures of stable particles that I showed you in the standard model picture, like electrons, muons, quarks that produce jets and things like that, not the Higgs itself. Okay, in terms of colliders, it's interesting to look at the discovery of various fundamental particles across the globe. So particle accelerators are everywhere. They're, of course, in the medical field. They're very prolific there for various treatments and things. It so happens that all the spin 1/2 particles, all the fermions were pretty much discovered on this side of the Atlantic, and all the bosons were discovered over here. So then there's, of course, the question is where's the spin 0 particle going to be discovered? And it's been a very heated race in the Fermilab, Tevatron, and CERN's Large Hadron Collider to try to find this Higgs boson. Oh, and I show here one thing that's important is, of course, these are actually scaled. These balls are scaled by the masses. So you can see the top quark, this is the scale that sets the scale of how much a proton weighs. Here's how much a top quark weighs. Here the W and Z particles which mediate the weak interaction are very massive, but not quite as massive as the top quark. And all the other quarks and leptons are pretty much small. So let's talk a little bit about the experimental facilities that are used to look for the Higgs. So here we have the Fermilab Tevatron, which is a collider that collides particles, protons and antiprotons. They circulate protons and antiprotons with a center of mass energy, which is 2 trillion electron volts. So it's a very, very high energy. And it's a matter-antimatter collider outside of Chicago here. The proximity to University of Illinois has meant that we could really play a really large role in the experiments that go on here. So here's the collider. We accelerate protons and antiprotons and circulate them in opposite directions, accelerate them to high energies, and then magnets are used to not only keep them in the loop, but also to focus them to collide at 2 different points, and we call those experiments CDF and D0, and the University of Illinois has worked for a long time on the CDF experiments. This experiment has ended, but results are still being reported, and I'll show you a few here. That's the ring here. This is at the scale. This is about 4 miles in circumference. Okay. Then we have the Large Hadron Collider, which is the world's current highest energy particle collider that spans between France and Switzerland. And here, this is 17 miles in circumference ring. So you sort of have to have these aerial space-like photos to really even see the experiment. And this is not a proton-antiproton machine. Oh, I should have mentioned, when I showed the standard model, we have all those are the matter particles, but actually every particle I showed there is doubled that it has an antimatter partner. Okay, so anyway, so then we accelerate protons around one direction, another beam of protons along the other, and we collide them at various points. And the points I want to just focus on are this point here called ATLAS, where we build very sophisticated, some of the most sophisticated instruments ever built. Here, ATLAS and CMS. These are the 2 proton that really are looking for the Higgs, the 2 experiments. And CMS has an experiment, which is a detector, which is quite different than ATLAS, but is really looking to do the same kind of physics. Okay, and so the collisions here, I showed you that that the Tevatron was a 2 TeV, trillion electron volt machine in terms of center mass energy. The design is going to be 14 TeV once we go to our design energy. Right now it's 8 TeV we're running at. Okay. Okay. How does this experiment work? Well, we have thousands of superconducting magnets and RF cavities so the superconducting magnets keep it on the circular path, and the RF cavities really give it the acceleration. So we collide. Now, one thing that's important to realize is that we're not colliding single protons on each other. That would be super inefficient. Instead, what we do is we take a bunch of 100 billion protons, and we slam it at another bunch of 100 billion protons, and we have a bunch of bunches that are running around the ring. So it's like throwing 100 billion apples at another bag of 100 billion apples. So proton bunches are colliding here 30 million times a second, and the experiment is a little bit underground here. So here's what the detector looks like. It's an enormous detector, and there are people here, sort of normal-sized people to scale. 7,300 tons is about as heavy as the Eiffel Tower, 100 million channels electronics, and it produces enough data to fill 100,000 of these arcane audio storage media called CDs per second. So it's an enormous amount of data that we're storing. And I wanted to mention what we do is the protons come in here, and they come in here. There's actually a beam line, and at the center right here, they're focused to collide. And what happens is then we produce possibly the Higgs, maybe other kind, more than likely we produce more mundane stuff. And eventually, once the collisions happen, they produce stable particles that then leave the interaction region. And we have a magnetic field that will bend charged particles, and we can track them and figure out what their trajectories are and so forth. Measure the energies. So we have calorimeters that measure the energies of the particles, and one of the calorimeters was built here at Illinois. Okay, so in terms of, okay. It's just one more picture of the detector. So this is with the inner detector pulled out, and you can see these toroids that eventually have the muon systems. And so one thing I wanted to mention here, some pictures where we have the hadron tile calorimeter was assembled here at Illinois, and Tony already mentioned that. Okay, so how does this look? So here's what we call event display. So we have, when we collide the particles, this is an actual event where we collided the protons came in, where proton beams came in, and were allowed to interact at this point here. And then we produce some spray of particles that our instrumentation can detect. And so these are stable particles in the end. And maybe the Higgs was produced here, maybe not. In this case, probably not. So there's a muon here. So there's a stable particle called a muon that leaves the interaction region and is tracked through our systems. And we have electrons that deposit their energy in our calorimeters that we can measure their total energies. We have this thing called MET, which is missing transverse energy, which means when we have things like neutral particles that are weakly interacting, like neutrinos, sort of ghost-like particles, they wind up just leaving our detector. And what they do is they leave a momentum imbalance. So you add up all the energies you see around here, and anything you don't see, you use it to infer the existence of one of these neutral weakly interacting particles, like a neutrino. So anyway, this is an example of the simultaneous production of a W and Z boson. The W then decays to an electron in one of these neutrinos, and the Z boson decays to 2 muons. And that's the kind of signature we look for. And so what we're doing for the Higgs search is we're collecting all of these particles, and we're looking at their energies and their directions, and we're using a little bit of relativity to put it all together and calculate something we call the invariant mass of the system, which is directly related to the mass of the decaying particle. So we look for once we put together all these objects, we look for what we call a resonance or a peak in the total invariant mass distribution of all these particles. That's really the crux of how we search for massive particles. Okay, let me go into just a brief little details about the Higgs physics in terms of production. So when we want to now, we need to do two things with the Higgs. Remember, it's unstable, so it decays almost immediately. We first need to produce it, then it decays. And we need to then look at the decay pattern and see whether or not we have the evidence for a Higgs. So the production at the Tevatron, these are things called Feynman diagrams, which really mean you can think of them as, you can read this, for example, as two gluons come in, and one gluon splits to a top-anti-top quark pair, which then fuses with the fact that this gluon also splits, so you have this little triangle here. It's a quantum mechanical process. And then the Higgs comes out. And I wanted to mention something very critical, that the Higgs field itself, in the theory, couples to mass in the sense that the larger the mass of the object, because the Higgs itself generates mass, the larger the mass of the object, the more strongly it feels the Higgs field. One analogy you can make with the Higgs field is think about it as like you're running in a sea of molasses, of sticky molasses. And as you run along, the molasses you feel that drag force from the molasses, and that's really what the Higgs field does. It couples to the particles and leads to your apparent mass because you feel an effective drag force from the Higgs field interactions. So anyway, Higgs couples proportional to mass. So this process here is actually the most dominant process for Higgs production. We call that gluon fusion because it's the fusion of two gluons. The Higgs field here, it couples to the top quarks most strongly, so this is the highest rate process. What I'm showing here is something we call the cross-section. Think of it as nothing more than for every collision, it's the probability, it's proportional to the probability of producing a Higgs. So the larger this number is, the more likely you're to produce a Higgs via that mechanism. So you can see the gluon fusion, this channel, is really the highest production mechanism as a function of the Higgs mass. And I forgot to mention that the standard model theory, we don't know the Higgs mass. It's not a prediction of the theory. So therefore, but once we hypothesize a Higgs mass, Everything else is determined. The couplings to other particles, all the properties of the Higgs is determined, but this is a free parameter in the Standard Model. So therefore, we have to scan through a whole bunch of possibilities. So anyway, versus this possible Higgs mass, here's this production cross-section. Then there's a case where two quarks can annihilate to produce a vector of one of these W or Z bosons, which radiates a Higgs. We call this Higgs Strahlung. And then there's other production mechanisms which are way down, so I won't really get too much into that, but it will become relevant later. Okay, so at the Tevatron, here's how we produce the Higgs, dominantly glue fusion, and then this associated production where Higgs are radiated. At the LHC, the main thing that happens is these switch. In fact, the dominant diagram is still gluon fusion, but we produce more of these, what we call vector boson fusion, where the quarks radiate these W or Z particles that fuse to produce the Higgs. Whereas this Higgs Strahlung process is subdominant to that. So you can see that here's the glue fusion production process, and here's this vector boson fusion process. And relative to the Tevatron, the LHC has a factor of 20 higher rated because of its larger energy to produce the Higgs than the Tevatron. And going to 8 and 7 TeV, which we did recently, there's sort of a gain that I show it there. Once we eventually go to 14 TeV, we get a factor of 40 in Higgs production. Okay, but we're not there at that design energy. So that's what I wanted you to take away from this, is there's a method, there are various mechanisms to produce the Higgs, and they have different probabilities of occurring. Once we produce the Higgs, it decays. And this is where our search strategy really gets tailored to the Higgs. So when we produce a Higgs boson, it can decay to all these different kind of stable Standard Model particles. Well, some of these are not all stable, like the W's and Z's eventually decay and so forth. But here's what we call the branching ratio of the Higgs as a function of the Higgs mass. Here we have, when we're at low mass, it predominantly decays to two bottom quarks. When we're at a higher mass, it predominantly decays to pairs of gauge bosons, of vector bosons. Okay? And then there's this process that's very, very important, which is GG here, stands for two gluons. This one's actually not that interesting, sorry. I meant here, photons. This one right here is so low rate, the fact that the Higgs can decay into two photons, but it also happens to be a relatively clean channel. So this is going to be an important channel. So really, for us, what we're going to focus on is the production of either W pairs, Z pairs, photon pairs, or bottom quark pairs in terms of how the Higgs decays. Okay. Now, in terms of the most sensitive channels, once we have a production of a particle like the Higgs, it can decay in a variety of different ways. And the ones I want to focus on here are the Higgs, where it produces either W pairs or Z pairs, and that can decay into two charged leptons like an electron or muon. That's what L means, a lepton. And these neutrinos, or it can decay to 4 leptons, which is a really, really clean signature. If we can get it to decay to 4 leptons, that'd be great. It also can decay to 2 photons. Now, one important thing I want to point out here, and there's these crazy diagrams you don't need to remember, but one thing that's interesting about the Higgs to 2 photon production is the fact that the photons are massless. And remember I told you Higgs couples to particles in proportion to their mass. So the Higgs actually does not directly couple to the photons. So when you produce a Higgs via this glue fusion process, the only way it can eventually produce 2 photons is basically having another one of these funny quantum mechanical loops where it goes through like a top quark loop because the top is really heavy. You see there's no coupling between the Higgs and the photons. Okay? So that's why this is a very rare process. Okay, so now what I want to do is I want to present the actual results. I had to give you a little bit of background to really understand what I'm going to show, but I hope I've given you enough now. So let me show you the latest Higgs boson results. First, I'm going to start with this is going to be almost primarily the ATLAS experiment, which we collaborate on here at the University of Illinois. And I'm going to look at the search where we look for 2 photons, and we look for a Higgs decaying to 2 photons. So the way we do this, remember I told you the way we look for a massive particle, this thing is going crazy. The way we look for a massive particle is we look for its decay products, we measure their directions and energies, we then add them together, and we look for a bump in something we call the invariant mass. So this thing, M gamma gamma, is taking the invariant mass, which is the energies and directions of the photons, and putting them together. And what a Higgs would look like is it would actually have a bump here. Okay, so what I'm showing you here is all the events in the data we've collected that have 2 photons in them that we've detected, and this is what their invariant mass looks like. and you see this huge amount of background, and then you see all kinds of other little blips, but you see this blip right here, which may or may not stand out across the other blips. One thing you see is that there's not really a whole lot of other stuff underneath it. So what you can do is you can take our background model, which is shown here, and you can subtract it out. So imagine taking this dashed line, which is coincident with the solid line, and taking the data, subtracting this background prediction. And what you get in the subtracted distribution is something that looks like this. Okay? It has a peak. Okay? I know it's not the most convincing thing in the world, but you clearly see that there's maybe something going on there. Okay? And this is where the statistics really come in. But you can hide everything in statistics. No, but you should see that there are a couple bins that are definitely high here. Okay? So now one thing I need to mention to you is the way we interpret this data. Here's what we do. Here's our data. What we need to do is we need to ascertain the probability that the background itself, that is, if we had no Higgs at all, imagine we have no Higgs, what's the probability, just by chance, that the background would fluctuate to give a signal that's as strong as what's seen in the data or stronger? We can evaluate that probability by running a bunch of little what we call toy experiments. But what we evaluate a probability the next time we take this data. What's the probability of seeing the background just by chance fluctuating, giving a signal as large or larger than what we see? That's what we call the p-value, and that's how we actually discover the signal. Okay. So before I get into that, just keep that in mind, though. And then I want to just show you some event display. So here's an event display of a 2-photon candidate, which actually has a mass right near that bump. By the way, that bump is right around 126, 127 GeV. And so you see what a photon looks like is it's not a charged particle. It just basically comes out of the interaction point and slams into our calorimeters, and the energy is measured. And we have there's happen to be back-to-back, and there's no real charged particle track that can be seen that's attached to that energy deposit. Okay. Now, here's where now I'm going to need to spend a few seconds on this slide, because this is going to set the tone for everything else. Here's how we interpret the data. Remember I told you we need to evaluate what's the probability by chance that the background would fluctuate to give a signal that we give what we see in the data as strong or stronger than what we see in the data in terms of the signal. So if we don't see a signal, what we do is we assume, let's say we don't see anything. We can then, if we don't see anything significant, that is, that probability is pretty small. It basically looks like noise in that mass distribution that I showed you. If this thing wasn't here and you just saw basically just fluctuations around the background, then what we would do is we'd say, oh, bummer, we didn't see the Higgs. What can we do now? We either just go home or we report some results. And what we do is we report results which are the limits on the production. So you can imagine here, if I go back to this mass distribution, even if I see nothing here, let's say over here, I don't really see anything, they kind of wiggle around, I can say, you know what, there's not a signal that's 10 times the standard model prediction here. There's not a signal that's 2 times the standard model prediction. So my ability to exclude a resonance at a certain mass hypothesis is quantified in this plot here. And this is in the production cross-section, or the probability of producing it relative to the standard model prediction. And 1 is the standard model prediction. So if this solid line, which is the observed exclusion, crosses this number 1, it means I can exclude standard model production at that mass. I hope that's maybe a little bit clear. So what we see here, what you would expect if there's no real signal, and by the way, the green and the yellow are sort of uncertainty bands, 1 and 2 standard deviation uncertainty bands. They quantify our uncertainty in that determination. Then what you would expect if there really was no signal there at all, you would expect that we'd be able to exclude possibly the standard model Higgs, and we'd sort of have an observed limit. That is, we're going to be able to say the production can't be higher than this line. So you would say we can exclude, we basically, if there was no signal, we'd see this black line kind of bopping around what we would expect. But if there is a true signal, then what we would see is a large deviation of our limit from the expectation. And that's exactly what we see at that mass. And that's just related to the fact that at this mass, there's a excess relative to our background prediction. So that's what these limits go. In the days when we didn't see anything, the limits were sort of this was the central plot. We're actually now moving towards something like a plot like this, which we call the local p-value, and this is exactly what I just described to you previously. This is what's the probability by chance of seeing an excess as large or large than I observe in the data, just by chance through fluctuations of the background, if there's really no signal in there. So if there is a true signal, that probability should be really, really tiny. Here you see it, just focus on the black line. You can see this probability of the background fluctuating to give our excess at this mass is like 10 to the minus 5. We refer to these as standard deviations. 4 sigma is roughly 1 in 37,000 chance. 5 sigma is 1 in 3.8 million, which is roughly the probability of rolling a die and getting 6 9 times in a row, just to give you a feeling. It's like a 1 in a 3.5 million chance that the background could fluctuate to give a bump that we see that's as large or larger. That's the best way I can explain it. So if there's a real signal in there, then the background only hypothesis is really improbable, and that's exactly what we see here. So in order to discover a particle in our field, we require there to be a 5 standard deviation excess, which says we have 1 in 3.5 million chance of basically just being fooled. Okay, that's a pretty big, that's a pretty stringent requirement. Okay, so anyway, so we see in this gamma-gamma channel that in fact there's a huge, very low probability for there to be no signal in here. Once we say that there's something interesting here, it's not quite 5 standard deviations. So in this gamma-gamma channel, I mean, you look back at this, would you hang your hat on saying this is a discovery? It's an excess, but So we're not quite at 5 standard deviations, but we're pretty close with just this channel alone. Now, if we interpret this as a standard model Higgs, then we can ask, what is the signal strength of that excess? And we can do it in standard model units. So if that bump was produced with a rate predicted by the standard model, we would see our signal strength be 1. And what it says is that in fact we see this signal with a little bit more than 1, but about twice the standard model in this channel. And there's an uncertainty band that's shown there in cyan. And then you can look at basically versus mass. You can look at the signal strength in a 2D plot, and you get a little ellipse, and I won't go that much into that. Okay, so here's where we're at. In this 2-photon decay channel, we see an excess that's not quite at the threshold of claiming a discovery in this channel alone, but we see a significant excess, greater than 4 sigma. Of course, what we need to do, and that alone is not going to be convincing, what we need to do is we need to look at other decay channels. As I showed you before when I was back here, I showed you that the Higgs can decay in a variety of different ways. One of them is to 2 photons, which is really low rate. But another way it can decay, depending on its mass, and if it's around 125 GeV, it actually has some chance of decaying into Z pairs. Here's the probability. It's about 10% branching, 10% probability that the Higgs will decay into Z pairs. So we can look in that channel, and what we see now is we take let's look at only 4 leptons. So each Z boson, we produce 2 Z bosons through the decay of the Higgs. Each Z decays to 2 charged leptons, electrons, muons. We then we observe these 4 leptons, which has a really, really low background. That's shown in red. We add together their energies and angles in a way that makes the invariant mass of that 4 lepton system we call M4. And what the Higgs would look like, a particle decaying to 4 leptons would have a bump or a peak in this mass distribution, and this is exactly what we see. Yes, there are other fluctuations and things as a low, but it's interesting to note that we're looking at an excess relative to the background prediction, which is red. Here's various Higgs hypotheses. But it's very notable that of all the places we could see an excess of the data above the background, it happens to be right where gamma-gamma says that it should be. So here we see an excess, which is not hugely significant, but confirms this gamma-gamma excess at exactly the same mass. So I want to show you a few event displays which are really, really cool in the 4 lepton channel. So we're talking about a Higgs decaying to 2 Z's, decaying to 4 muons. And here's what we're seeing is here the protons are coming in, here's the interaction point, and then these muons come off and are detected with our muon systems. And you see 4 of them. And you actually see a whole bunch of what we call pile-up interactions, which really are because we're colliding 100 billion protons on 100 billion protons, and you get all kinds of interactions where the Higgs doesn't come from. And this just shows an example of, instead of decaying to 4 muons, one Z decays to 2 electrons, the other Z decays to 2 muons. And this shows where the muons go through the muon system, and the electrons go and make energy deposits in our calorimeter. And then we have an example of a 4-electron event where all the energy is deposited in our calorimeter. Okay, so we have some really striking 4-lepton events that are consistent with the Higgs the excess that's seen in the gamma-gamma channel. Okay, now I want to show you those same kind of plots now, except for the Higgs to ZZ search that I just described. And what you see is the same kind of limit plot, where here's the expected limit, and here is the observed, so focus on the observed limit. We see a deviation of the observed limits from the expected limit shown in the dashed, which is right around the same mass as we saw the gamma-gamma. If we can ask, what's the probability of that just happening by chance? So again, what's the probability that this red background will just happen to give an excess that's as large or larger than what's seen in the data? We can ascertain that probability through a bunch of pseudo experiments, toy generation. And we see that if we look in all masses between 110 and 180 GeV in the Higgs mass, we see this probability that the background alone giving that excess is less than 1 in 1,000. It's a little over 3 sigma. It's 3 standard deviations. You can make a... Okay, so we see an excess of events right around where gamma gamma sees it, and then we can ask what is the signal strength, what's the rate relative to the standard model prediction, and it happens to be right around 1. So it has a rate of production which is right around the standard model. Okay, we can put all these, so these, I just described 2 decay channels to you. We can combine these. So you think of, okay, so we see a bump in some mass distribution in gamma gamma. We see another bump in the 4-lepton mass distribution. What's the probability of seeing that both these independent channels seeing the same kind of excess in the same place? You can combine them statistically and ask, what's the overall probability with those 2 channels that the background would just happen to, by chance, give that kind of signal? Now, oops, interesting. Okay, doesn't matter. I was going to show you a whole bunch of different channels that go into it. My group worked on a couple of these different channels. The main point I want to make is that when you put all these different decay channels, I talked about gamma gamma and 4-lepton, but there are other ways to look for the Higgs, and we contributed to a number of these. And we can put it all together, and now I'm looking at a huge mass range. Look, between 100 GeV and 600 GeV. I say, here's my sensitivity to see the Higgs. It's well below the standard model. That is, I can see a standard model Higgs all along here. If it's there, I'll see it. And what you see is that you see an observed limit, which is consistent with the expected limit. That is, there's no signal here. And whoop, you see this huge excess here, right around 125, which means that all the channels together confirm the excess. Doesn't mean each channel sees an excess, but together there's a large excess that's consistent. So what we can say is anywhere our observed limits cross this 1, we say we've excluded the standard model Higgs at that mass. And you can see now we're in a state where all standard model Higgses have been excluded except for in this very narrow sliver here. And in fact, when you combine it all together and you ask, what's the probability that the background by chance could produce a signal as strong as we see in all these channels? The probability is less, it crosses this threshold of 5 standard deviations, which means we have less than 1 in a 3.5 million chance that by chance this would have happened. If there was no signal, just by chance. So this is beyond our threshold for discovery, so we claim we've discovered an excess consistent with a new particle at this mass. We can turn it around and look at something we call, I haven't showed this kind of plot yet, but we can turn this plot, the p-value plot, and turn around, just look at the local significance where we allow the deviation to be either plus or minus. And this is pretty much like an inverted version of what I just showed. But you see that the excess is the significance of any Higgs-like excess is pretty much 0 everywhere except for right here where it's over 5 standard deviations, right around 126 GeV. This is the same plot I just showed, except for broken down by all these different channels. And I show this plot it's so busy, I show this plot not that you follow everything, but I want you to get the feeling for, there are literally dozens of people that work on each one of these channels. And I have students working on various channels. There are a lot of people, this is an enormous effort this is hundreds of people within our collaboration, get together and look in different channels, and then we put it all on some big meat grinder and we have a discovery. It's a little bit more better than how sausage is made, but okay, so we put it's a big grinder and a sausage comes out. All right, the signal strength, combined signal strength looks like this. We see consistent with the standard model prediction, that is at 1, and we see a 0 signal strength everywhere else. If I zoom in just for a second, I'll just scan through these and I zoom in and close. This is just, I was showing you before from 100 to 600 GeV. If you want to know, I can tell you later why we don't go further out, but it's 100 to 600 GeV. If I zoom in now between 1 and 150, which basically is a zoom in of this region here, you can look and you see this huge excess in the observed limit. You see that the p-value, which is the probability the background would fake us out, is less than 5 standard deviations. The significance, again, is above 5 standard deviations. And the signal strength, combining all of our data, is above the standard model prediction, but in fact, given the uncertainty band, that is our uncertainty about how, what the signal strength is, in fact, it's consistent with the standard model prediction. That's why we call it a Higgs-like particle, because we've seen something that has a lot of characteristics of this long sought after Higgs boson. We can then look at a plot here where we take all different channels that are sensitive, and we can just look at the signal strength in each channel. And I just want to mention they're all pretty much consistent with the standard model. The gamma-gamma I showed you was about an excess of about 2 times the standard model, as you can see here. Okay, so that might be telling us something interesting, but we don't have enough data yet to know. We can then ask, what's the consistency between our 2 most sensitive channels, Higgs to gamma-gamma, like I showed you, and Higgs to ZZ to 4 leptons? And these are versus a function of the Higgs mass and the signal strength versus Higgs mass. We can make a 68% contour and a 95% contour, which just tells you 68% of the time you should be in here, 95% of the time you're in here, and you can ask, what are the consistencies? Are these 2 measurements consistent in their signal strength? And in fact, they deviate a little bit, but their ellipses overlap, and so probably they're consistent at this level. But if they start to deviate, then something very interesting happens. That's the ATLAS case for discovery of a new particle. I want to show you now, I'm not going to go into detail, but just show you for our friends around the ring. Remember I mentioned that the protons at the LHC are set to collide at 2 points on the ring. One of them is ATLAS, the other one is CMS. And they have a sort of a detector that's quite different than ours, but the same kind of motivation. And what they see is they also look at their data, and they see in the gamma-gamma channel and the ZZ channel an excess at exactly the same mass that we see. And they see it with 5 standard deviations of significance. So now you have an completely independent experiment across the ring who sees a signal that's exactly in the same, well, essentially exactly in the same place where we see it. And their signal strength is less than the standard model, so you could say if the standard model is true, they got a little unlucky, and we got a little lucky, that's c'est la vie. They see a signal strength which is pretty much consistent with the standard model. So they have results that are very similar in character to us. They see that they confirm, I don't want to say confirm because it's really a joint thing, but they see the same kind of signal that we're seeing. Finally, I wanted to mention the Tevatron. Tevatron stopped data collection, but Kevin has worked with his students on the Higgs searches at the Tevatron. They gave it their absolute best shot. The only issue is that the energy is just not high enough to be competitive with the LHC, for the standard model Higgs at least. But you can ask, what does the Tevatron see? They came out with their final results on the Higgs. And in fact, they are sensitive to this Higgs to BB bar, where it decays to 2 bottom quarks production primarily. And when you look at their data, here's their expected limits, here's their observed limits. They see a significant, about 3 standard deviation excess in the same mass region that the LHC sees. Just not with the 5 sigma significance you'd be required to claim a discovery, but yet consistent. Okay, and then you can look at their p-value, and they basically have, like I said, around about almost 3 sigma at the mass. So if you look at the observed. Now, has the Higgs been observed? We're not sure yet. So what has been observed? Well, what we've seen and what we claim is that the ATLAS and CMS collaborations have independently observed a new fundamental particle with a mass around 126 GeV that resembles the Higgs boson, has properties that resemble the Higgs boson, so we call it Higgs-like. But we're being careful because we don't know if it's the fundamental scalar that's in the standard model. It may be something completely different. But it has characteristics of the standard model. So the existence of this new particle is consistent with the events that are seen at the Tevatron and their excess. So now we can add to this picture the Higgs, and the Higgs really has been discovered at the LHC, and we don't know actually if it's a scalar particle or a spin 2 particle. We know it can't be a spin 1 particle because of a theorem called Yang's theorem, which tells us that you can't have a spin 1 particle decaying to 2 identical spin 1 bosons, but okay, that's a detail. So we still don't know whether or not it's a spin 0 or spin 2. But we're going to be looking. Okay, so this made a big splash, as you heard from Dale, said he stayed up all night watching it. We watched it from my lab with my students with some pizza and some root beer. Watched the event from 2 to 4 a.m. And so here's a picture in the New York Times, the Science Times, which was the auditorium there at CERN. And you see the Director General pumping his fist in celebration that they discovered this particle. This has really been an international, this experiment has, as you can imagine, has a real international flavor to it. I mean, there's lots of people that have contributed to this, thousands of physicists. So right now we see this 5 sigma excess. And they're really the accomplishments of of 20 years of talented work and lots of people and help from the funding agencies for sure. And more general, the results that really result from the ingenuity, the vision, and the painstaking work of the community. The University of Illinois has made major contributions to this. So our contributions, the University of Illinois ATLAS group, really played a vital role in the Higgs discovery. So I want to tell you a little bit about how that works out. Well, we contributed, in order to do this, we need to construct a detector, and we contributed to the detector construction and commissioning. So you heard about the Tidal Hadron Calorimeter was built here in Illinois. We have, Tony's group has worked on the muon data quality, and I've worked in the trigger system. We also have a major effort on data processing and simulation. So we have a computing effort here to build tier 2 and tier 3 computing resources. I'll say a little bit more about that later. And then the data analysis, of course, we've actually done, aspects of the data analysis that were key to this discovery. Of course, there's the legacy of the Tevatron is the Tevatron actually played a huge role in this discovery too, in the sense that the accelerator and the detector technologies developed the Tevatron, and equally importantly, were the data analysis techniques and software that were developed at the Tevatron to search for the Higgs. Over many, many years, these tools and software were honed and sharpened and looking for the Higgs at the Tevatron. And were literally ported to the LHC, all these very sophisticated techniques. I used code that I looked for the Higgs on CDF. So the ability for the LHC to do this so quickly is in part due to the experience from the Tevatron and the CDF and D0 collaborations. And our theory group played a significant role in just showing the way in terms of what are the channels we could look for. So Scott Willenbrock wrote some very seminal papers, unfortunately he's not here, describing the role that the Higgs, how you would search for the Higgs in a hadron collider, and continues to help us in understanding what we should be looking at at the Tevatron. And Tim Stelzer was the father of a program called MadGraph, which was really a critical tool used to simulate the data we would expect for a variety of different phenomena. So what I want to do at this point, I'm getting close to the end. At this point, I just want to give you a feeling for just the level of effort even locally here. So if you could just please do me a favor, and if you're working on the ATLAS or you're one in the theory group working on LHC phenomenology or the CDF group, just stand up for 1 second. You can sit right back down. So if you just do that. Okay. Thank you. That was painful. Okay, thank you. And in addition to the people here, we actually have most of our people in the LHC experiment are actually at CERN, working hard. And so here's a couple members of our group at CERN, postdoc students and researchers. What's next? Step 1, celebrate. In progress, right? So that's what this is all about. It's really not about me giving you some hopefully not dry description. Really, it's about celebrating what's really a truly big discovery. In addition to that, looking for this new particle in other decay channels. I showed you gamma gamma and ZZ, but actually, one thing that's coming out really relatively soon is a channel that myself and students really worked on, which is K to WW, to diboson pairs in WW, and that's something which is another channel that's going to add to the intrigue of this measurement, and all kinds of other channels that actually people in our group are working on. So that's one thing. Just look for it in other channels. The other thing is study the properties of the particle. So at some point now, this Higgs is going to be a background to new physics searches at the LHC. So the thing we've been looking at, the machine was not exclusively built, but certainly a big part of why this machine was built has been discovered, or something very much like it. And so now we need to study the properties. And I list a bunch of different properties here, but I want to just say, so study the properties of the new particle, determine if it is the Higgs boson in the Standard Model, because theories beyond the Standard Model can predict multiple Higgs bosons, different spins, and so forth. So we want to know, is this thing we just saw the Higgs boson or imposter? So where do we look? So out of the fog has emerged this agent of electroweak symmetry breaking, we think maybe. And this is fundamental. It's about the origin of mass itself and the ability of the universe and the life and life itself to be as we know it. So is this the agent of electroweak symmetry breaking? So the thing we want to do is study this now, really carefully. So we want to look closely at the agent of electroweak symmetry breaking. And one of the things you notice immediately, or I notice immediately, is that such a beautiful, fundamental object this is would not be a Yankees fan. So like, so this shows you immediately what this thing that was observed as Higgs probably an imposter, and the real thing is yet to be seen. Okay. So anyway, I want to just mention, so things we're going to measure right now are the mass, the spin. You knew you shouldn't have sent me that figure, that picture now. You're regretting it. The mass, the spin, its charge parity properties, symmetry properties, also the couplings to other particles. One of the cool things is you saw those different ways of producing the Higgs. They involve couplings between the Higgs and the fermions, that is, the quarks. And also they involve, other protection mechanisms involve couplings of the Higgs to the vector bosons, the W and Z. So we can start to look at different production mechanisms and understand whether the pattern of couplings, the decays as well as the production rates, match what we expect in the standard model. If not, we've discovered something new. Also, many of these theories beyond the standard model predict additional Higgs-like particles. Okay, it's wonderful, we discovered this Higgs-like particle, but what if it is the Higgs? And what if that's it? We've discovered the Higgs, and we keep looking in higher energies, and we just see nothing else new. That holds a lot of people up awake at night. I'm still on the high from just seeing it, but okay, maybe I'll start to lose some sleep. But the thing that keeps me maybe sleeping at night is the fact that the standard model with a Higgs is still unsatisfactory. It cannot be our final theory of nature, because it has a lot of deficiencies, and I don't want to go in detail, just to say one of the things that happens is if you run this Higgs up to high scale, it has some instability against its own corrections to various particle corrections, virtual corrections to its mass. You know how we said at high temperatures the weak and the electromagnetic forces are unified into an electroweak force? We haven't yet been able to do that with a strong force, this SU3 part of the symmetry. So there's no further unification of the forces at high energy within the standard model. That's yet to be explained. There's no satisfactory explanation of the predominance, the vast predominance of matter, antimatter, matter over antimatter in the universe. One of the reasons why you haven't annihilated into photons sitting in your chair is because we're all matter. There's too many free parameters. The Higgs describes how we create the masses of the fermions, but they involve something called Yukawa couplings and have free parameters that are just unsatisfactory. It's not really descriptive at all. It doesn't include, of course, gravity not included, like I said before. And also, there's no explanation for what we know to exist, which is dark matter in the universe or dark energy. So I just remind you about what dark matter is. The fact that if you look at the rotation dynamics of galaxies and the cosmic microwave background, and you look at stars and use the fact that we see lensing phenomena, so basically light being bent around massive objects that don't even need to be luminous. All these things point to a very large fraction of our universe having non-luminous massive matter. So what is dark matter? We don't know, but we have a lot of ideas, and one of them is supersymmetry that I won't talk more about. So no matter what, the universe, what we've discovered with the Higgs and the standard model really only describes 4% of the known universe. 23% of it is dark matter that the standard model provides no explanation for, and the rest of it is dark energy which nobody provides explanation for. So there's still a lot of puzzles, and maybe the Higgs is one of these next steps. I'm going to just end with a slide or two, and then I'm done. I wanted to mention that there are some real challenges ahead in studying the Higgs properties. One of them is called pileup. Remember, we collide 100 billion protons on 100 billion protons, and if we want to collect data more and more rapidly, we squeeze more and more protons into those bunches. And eventually, when those big bags of apples cross each other at our experiment, we start to see lots and lots of interactions happening in one crossing of those bunches. Here's a case where already in the data we see 25 pileup interactions. This is looking in the Z direction, so along the proton beam line. And here happens to be a Z boson produced decaying to 2 muons, but you'd never know it if I didn't highlight it, right? So being able to suppress all this other junk of extra collisions that we don't care about, like that don't involve the Higgs, is a real challenge. And so my group's developing along with collaborators, some new trigger electronics to try to deal with that. Another big challenge is the challenge of big data. The LHC produces 15 petabytes of data a year. This is a major, major challenge. So you see it being, it's served to the graduate students who are hungry and waiting for Higgs discovery and now Higgs property. So, this takes some work, right? And so, one of the major challenges is really in data collection, cataloging, storage, delivery, and so forth. And so we actually spearheaded an effort with Dave Lesney, who's sitting here, and a new collaboration with the NCSA to create a Tier 2 computing facility, which eventually become quite large, over in the campus cluster to help address these challenges. And in fact, the data that was used in the Higgs discovery flowed through our Tier 2 facility over at NCSA, so we contributed in that way. There's another thing that's really challenging, which I invented a word called socio-scientific challenge, it's a new word, about big collaborations. I think this is a real challenge. I don't want to belabor the point, but it's almost becomes a Where's Waldo kind of thing. And it's really difficult sometimes for the students to adjust and thrive in such an environment. I don't know, does anyone see Waldo? Almost right up there, right? So you can see this poor graduate student in the ATLAS collaboration just saying, hey, can anybody hear me? Am I ready to graduate yet? So this is a real challenge for our field, and I think I've personally had to adjust how I sort of train the students I have to handle such an environment. And in fact, just for me, I actually did a little thing where I charted this is the number of Neubauer collaborators versus time, and looked to see, here I started, and there's many RU students here, and I started in the RU program at Penn State with 5 collaborators, then I went on to this neutrino experiment with 80, then CDF experiment with 600, and now I work with 3,000 collaborators, so in a few years I'll be working with the entire state of Illinois or something, right? So this is a real challenge, and Einstein never had to deal with this. Okay, I'm tired, so conclusions and outlook. Finally, I just wanted to summarize to say that what we've done is accomplish something really, I think, phenomenal and an international accomplishment, where we've discovered a new elementary particle resembling the Higgs at 126 GeV. Our group really played a vital role in this discovery in many of the ways I described to you. The implications for this discovery are still unfolding because now we're just starting to, having discovered this particle, we're trying to measure its properties, and we'll see how that goes. Will this be the end of an era, or will this really be the start of a new beginning? And I very much think it's going to be the latter, optimist. But in any case, this discovery really reaffirms, I think, the vitality of particle physics. And there are other ways that we can try to study, look for non-standard model physics. And many of our collaborators are also looking at this, not just in collider physics, but also looking at precision, looking for very rare phenomena and things like that, looking at the cosmos with some of these big telescopes. So there's many ways we can do this. But I think, particle physics is a vital area of research. And I just wanted to say, let's not forget that while the Higgs is playing a central role right now in the PR out of the LHC was, it's a potential discovery machine. It's not all about the Higgs. So, one of the worries out of CERN was, well, okay, so you've built this machine, you've discovered the Higgs, that's what you were designed to do, so where's the switch? Where do I find it, right? Let's turn it off. It's nothing like that. This is just the beginning. We've discovered the Higgs, but really it's about studying the Higgs and it's about looking for possible new physics. It really is a potential discovery machine. And I think we have an exciting voyage ahead. Maybe we'll find more Higgses. Maybe we'll find extra dimensions. Susie, who knows what that thing is. So it's really an exciting time ahead. And I just wanted to make some acknowledgments I really want to thank the Department of Physics, the College of Engineering, and the university in general for support of this research, and of course our funding agencies, so I list our grant sources there. Okay, thank you everybody.